Hi, hope you've enjoyed the first couple of segments of this Petrophysics for Dummies session. I won't keep you too long. This next section is on porosity. Remember, I'm going to be a bit tedious and ask for subscriptions and subscribe and like and all that kind of stuff as I set up my new Petrophysics Rocks YouTube channel. Hopefully you've seen the first two installments of this session, but this one is called porosity. That's the amount of holes in the pore space. A lot of people kind of think these oil fields have big tanks, big caverns of oil below the surface. You just drill into them and there's a big cave full of oil, but actually it's not. It's in the rock basically, and it's all sort of soaked up. And this is my reservoir analog. This is a piece of bread, you know, and you could imagine this all soaked with oil or something more savory perhaps, but it stays within the pore spaces here. It all soaks into the rock fabric. And this next chapter is about how we measure those holes downhole, so that when with thousands of feet below the Earth's surface, how many holes have we got? How much oil can we hold? Okay. Let's get on with the second. Where are we now? There we go. The porosity one. There we go. Yep.
So the next element that we need to know, knowing the rocks, is what is the volume available to hold fluid. So the volume, the term, remember, is that porosity term. What porosity is available in these rocks. So if I put some holes in these rocks now, you can see that we've got this pore space, and we need to make some measurements to quantify how much pore space is available to hold fluid. So we make another type of measurement. We put another different type of wireline tool down in our wellbore, and we are now porosity logging. And by convention, increasing porosity is shown from right to left, so that the higher the porosity, the curve appears on this side of the track, and the lower the porosity, the curve appears on that side of the track. But there are a number of different porosity measurements, and I'm just going to touch on three right here. So there are three ways that we can measure porosity in our rock. Now these are generally active devices, if you like. These tools do something to the formation and they measure a response. So they're not passive devices, just listening. They actually stimulate the formation in some way and then measure the response to that stimulus. So the first measurement I'm going to talk about is the sonic log. So here we send sound waves through the rock and see how long the sound waves take to get from the transmitter to the receiver, and the amount of time it takes to travel through this rock tells us something about the properties of that rock. So if it takes a long time for the sound wave to travel through that rock, that means there are lots of holes in the way. You may know that sound travels much quicker through solids than it does through liquids or air. So if there are more holes in the reservoir, that tends to slow the sonic signal down, and when we make a porosity measurement, you'll see that the sonic slows down here in the porosity, high porosity zone, and in the carbonates, which generally have lower porosities, we see that it's much faster velocity, so that's a lower porosity. And here in this sandstone here, you'll start to see that actually, although this is the same rock type, we know that from the gamma ray, you can see that actually it's a little bit faster, so therefore it's a little bit lower porosity than this sandstone up here. Then when we get into the shales, rather interestingly, that shows very high porosity, very slow shales, and so you might interpret that as quite a high porosity. Now that's interesting because actually shales don't have a very high effective porosity. They may have a high total porosity. They may contain quite a bit of water, might be quite uncompacted, but so less rock. But actually, as I mentioned to you before, that porosity is not connected oftentimes, and therefore it's not what we call effective porosity for oilfield purposes. Anyway, we've got some other measurements to make. The next measurement I'm going to talk about is a density log. Now, the density log, again, is an active device that beams gamma rays at the formation. And these are radioactive particles, if you like, these gamma rays. And if we have a lot of rock in the way, a lot of solid rock in the way, then we bounce back a lot of those gamma rays. It means the lower the porosity. We've got more rock in the way. So the less counts we get at the detector, it means the more rock that's in the way and the lower the porosity. So we make a density log measurement. Again, we scale it in a similar way. You'll see once again that this upper sandstone interval has a lower density than this lower sandstone interval, which has a higher density. So it has a higher density, more dense, more rock in the way, less holes. Here is a low density rock, and it has lots of holes in it, high porosity. And here we come into the shale, and we have, in this case, a slightly higher density, more rock to fluid pore size, if you like. So the neutron log emits neutrons into the formation, and neutrons react with hydrogen in the formation, and hydrogen is encountered in the water and the oil. And so therefore we can say that the neutron log, if you like, is a fluid affected log. It sees the amount of fluid in the formation, and depending on how much fluid is in the way, it depends on what signal reaches the far detector, and then we can infer from that that there must be a lot of fluid in the way or a lot of porosity in the way. So the neutron log measures the fluid porosity, if you like. So we make the neutron measurement. We just put our neutron log in the wellbore, record it coming out, and again you see that we have a lower porosity into the carbonate, even lower porosity, then up into this upper sandstone interval, which has quite a reasonable porosity, and then again we see quite a bit of water in these shales, and so therefore we have an increase in apparent neutron porosity, rather like the sonic, in the shales. So in summary then, I guess the neutron is a fluid porosity log. The density measures the rock more directly, and the sonic wends its way through the pore, both matrix and fluid, and depending on a combination of effects, how it transmits through there is how you infer the porosity. So when we plot these things up on the suitable scales, we can get our friendly geologist to come along, and we scale them in this part of the world such that we have a few porosity units worth of separation between the density porosity and the neutron porosity, because that gives our geologists something to do and colour those in quite nicely. So here we see sandstone that we coloured in yellow, and here we see a mud rock that we've coloured in green, and this crossover, the logs are scaled to give this kind of crossover. Now in the States they apply slightly different neutron scalings, and I guess their geologists don't like colouring in as much over there. So that's the porosity. So the logs we've got so far, we know the rock type, we know the porosity, we know how much holes there are in the rocks, and in combination with some colouring work we can also get a further insight into the rock type as well from these porosity logs. You'll see that in the carbonate rocks, the density and the neutron logs tend to overlay. Sandstones, as I said, we scale them to give this sandstone separation, and in shales or mud rocks we get this reverse separation. So that gives us additional lithological information.